This is the second video in our two-part series on molecular geometries. In this video, we will look at the molecular geometries that come about from the trigonal bipyramidal electron geometry and the octahedral electron geometry. When there are 5 electron groups around a central atom, we are working with a trigonal bipyramidal electron geometry. And if one of those is switched out for a lone pair of electrons, they will occupy the equatorial position because there is more room. Essentially, if we have a trigonal bipyramidal geometry and one of the electron groups is a lone pair, we could either put them in an axial position or an equatorial position. They will end up in the equatorial position because there is more room. In the equatorial position, the angles between the lone pair and the other atoms are as follows. You can have your lone pair and the axial groups form a 90-degree angle, and then you have two sets of 120-degree angles between the lone pair, the sulfur, and the fluorine, as well as between the lone pair, the sulfur, and the other fluorine in this particular example. If we were to have the lone pair electrons in the axial position, you would have 3 sets of 90-degree interactions as opposed to the 2, and you'd have one at 180. The 3 sets of 90-degree interactions would cause a greater deal of repulsive interactions than you would see in the case that we actually do see, which is the lone pairs being in the equatorial position and having only 2 sets of 90-degree interactions. Because your lone pair of electrons push more than bonding pair, that causes the groups in the axial position to push away from your lone pair electrons, as well as the other 2 axial to push away from the lone pair. The result is that the bond angles between the equatorial positions, so this angle here, becomes less than 120 degrees. The bond angles between the axial and the equatorial become less than 90. And the linear would be slightly less than 180 degrees axial to axial. So when there are 5 electron groups around the central atom and one is a lone pair, we call the resulting structure a seesaw shape or sawhorse, though the seesaw is the much more common name. The reason it is called a seesaw is if you place these 2 on a table, then the other 2 groups, those in the axial position, would form a seesaw-like shape. If we swap out another bonding group for a second set of lone pair electrons, so when there are 5 electron groups, we're still working with a trigonal bipyramidal electron geometry, and they're around the central atom, and we have 2 that are lone pairs, they're going to occupy the equatorial position because, again, there's more room in the equatorial positions. So when there are 5 electron groups around the central atom and 2 lone pairs, we get a T shape for the molecular geometry. Your 2 sets of lone pair will occupy the equatorial positions, and your remaining atoms form a T. So if you were to take this and rotate it 90 degrees, it ends up looking like a T, and so it is called T-shape. So again, the electron geometry is trigonal bipyramidal. You have 2 electron groups, and the resulting molecular geometry is called T-shape. Finally, if we replace 3 electron groups in our trigonal bipyramidal geometry with lone pair electrons, they're all going to occupy an equatorial position. So when there are 5 electron groups around the central atom and 3 are lone pairs, they will occupy the equatorial position, again because there's more room. When there are 5 electron groups around the central atom and 3 are lone pairs, we call the resulting structure linear. And that's because when you discount or no longer consider these lone pair electrons and are only considering the atoms will fall along a straight line. An example is xenon difluoride. This shape here, the fluorines occupy a line with the xenon in the center. If we add an additional electron group onto our previous structure, we end up with 6 electron groups, giving us an octahedral geometry. When there are 6 electron groups around a central atom and we start adding on additional electrons, the first one, it doesn't matter where you place it. The reason for this is that in the octahedral electron geometry, each one of your groups occupies an equivalent position. So we can replace one of them with our lone pair electrons. When we start replacing additional bonding pair with additional lone pair, they will go on opposite sides to each other. When there are 6 electron groups around the central atom and one is a lone pair, as is the case here, the resulting structure is called a square pyramidal shape. The reason it's called square pyramidal is because if we ignore the lone pair electrons, we get a shape that looks like this, where we're looking at just where the atoms are. The base forms a square, and then the upper fluorine, in this case, forms the apex of the pyramid. The bond angles between the axial and your equatorial, as well as between the equatorial, are going to be less than 90 degrees. Again, because your lone pair pushes these fluorines up, making them closer together. If we now swap out an additional bonding pair for an additional lone pair, we will have 6 electron groups around the central atom and 2 lone pair of electrons. The result is called a square planar shape. The reason it's called square planar is because when we're considering only the atoms, they form a square and it falls along one plane. All the atoms are in one plane. The angles between the equatorial positions are going to be 90 degrees. And the reason for that is these 2 sets of lone pair electrons are going to push down with equal force. The result is that the fluorines actually stay in place as compared to an octahedral electron geometry. Let's now summarize our different electron and molecular geometries. The way that we're going to categorize them is based on the number of electron groups. If we have 2 electron groups, we will have 2 bonding groups, giving us 0 lone pairs. The electron geometry and the molecular geometry are called the same thing. They are both linear. The approximate angle is going to be 180 degrees. An example of this is carbon dioxide. If we have 3 electron groups, we have 2 options. One where we have 3 bonding groups and one where we have 2 bonding groups. In the case of the 3, that would leave 0 lone pair electrons. We would have an electron geometry of trigonal planar and a molecular geometry of trigonal planar. The bonding angles will be about 120 degrees. If we swap out one of our bonding groups for a lone pair, the electron geometry will still be trigonal planar because that's where the electron groups are. However, when we're considering the molecular geometry, we ignore the lone pair, and so the resulting shape will be a bent shape. The example here is sulfur dioxide, which takes this bent type shape. Next, if we consider 4 electron groups, there are 3 different options depending on the number of lone pair electrons that you're working with. If all of the electron groups are bonding groups and we have 0 lone pair, then the electron geometry is tetrahedral and the molecular geometry is tetrahedral. The bonding angles will be about 109.5. An example of this is methane, CH4. If we now swap out one of our bonding pair for a lone pair, the electron geometry is still tetrahedral because that's where the electron groups are. Both your bonding pair and lone pair count as electron groups. So the electron geometry stays tetrahedral, but the molecular geometry is now trigonal pyramidal because the shape has a triangle on the bottom and the central atom forms the apex of a triangle. The angles will be less than 109.5. Finally, swapping out one additional lone pair, so we have 2 bonding pair and 2 lone pair, the electron geometry is still tetrahedral, but the molecular geometry is now bent. Our example is water, which has a bond angle of less than 109.5. In terms of the things that you will need to know, it is a good idea to memorize this section that is within the red box. You should be able to figure out the number of electron groups, the number of bonding groups, the number of lone pairs from the Lewis structure. and then using that information be able to determine the electron geometry and the molecular geometry. And from a molecular geometry, you should be able to specify roughly the approximate bond angles, being 180, 120, less than 120, you don't need to be more precise than that, 109.5 or less than 109.5. Now moving on to the larger groups, if we have 5 electron groups, there are 4 different options. We could have all of the electron groups be bonding groups, which would give us a trigonal bipyramidal electron geometry. The molecular geometry is the same because all of our electron groups are also bonding groups. We have 2 different sets of angles. We have between all the equatorial, they will all have bond angles of 120 degrees, and then between the equatorial and the axial, these will be 90 degrees. Swapping out one of our bonding groups for a lone pair, our electron geometry will still be trigonal bipyramidal, but now our shape, our molecular geometry, will be seesaw. The angles are similar to those of the trigonal bipyramidal, except they contract slightly, and so our angles around the equator, the bond angle, will be less than 120, and for our axial to equatorial angles, this will be less than 90. The name again is seesaw because if you take your equatorial positions, lay them on a table, it looks kind of like a playground seesaw. Swapping an additional bonding pair for a lone pair, giving us 5 total electron groups, 3 bonding groups, and 2 lone pair, we still have a trigonal bipyramidal electron geometry. The molecular geometry is now called T-shape, and the angles for all of our bonding groups is going to be less than 90 degrees. So it is called T-shape. These are your axial, and then this is your last equatorial. If we replace one additional bonding pair for a lone pair, giving us 2 bonding groups and 1 lone pair, our electron geometry remains trigonal bipyramidal, our molecular geometry is linear, and our bond angle will be 180 degrees. Finally, expanding to an electron group of 6, we have 3 different options that we will be considering. The first is when we have 6 bonding groups and 0 lone pair. Because we have 6 electron groups and all of those electron groups are bonding atoms, both our electron geometry and our molecular geometry are going to be octahedral. The angles for octahedral are 90 degrees. If we swap out one of those bonding pair for a lone pair, giving us still 6 electron groups, 5 bonding groups, and 1 lone pair, our electron geometry stays octahedral, our molecular geometry is square pyramidal, and the angles in our square pyramidal geometry are going to be less than 90 degrees. Finally, swapping out one more bonding group for a lone pair, giving us 6 total electron groups, 4 bonding groups, 2 lone pair, we will still have an octahedral electron geometry, but now our molecular geometry will be square planar, and the angles between our bonding atoms are going to be 90 degrees. Again, the important component is that which is within the red box. This is the part that you should be memorizing for this class. You'll need to be able to tell the number of electron groups, bonding groups, and lone pairs for each one of these types of configurations.